In this lesson, we'll go beyond supervised learning and talk about various other machine learning settings. For example, we'll look at low-labeled machine learning settings where we have only a few labeled examples, possibly with a larger amount of unlabeled examples. We'll also talk about pure unsupervised or self-supervised learning, where we'll try to learn effective feature representations using unlabeled data only. Thus far, we've really looked at supervised learning, where we have a large labeled dataset X and associated labels Y, typically coming from human annotation. In deep learning, we want to learn a function that maps from X to Y, typically as a conditional probability, the probability of the label given the data. However, annotation of data is costly, both in terms of time as well as monetary cost. This is because you have to pay people in order to annotate manually each example. And this can really add up if you have hundreds of thousands or millions of examples. So we may want to consider machine learning settings where we assume that we have much less labeled data. We'll look at a few common settings. In semi-supervised learning, we have some reasonable amount of labels per category, let's say 10 or more. However, we also have a large set of unlabeled data. This is again under the assumption that obtaining unlabeled data is much easier, for example, by just scraping the internet without having to pay the cost of annotation. In few-shot learning, this is taken to extreme. Specifically, we have only 1 to 5 examples per category. In the vanilla setting, we also don't have any unlabeled data, but it is assumed that we have some larger labeled auxiliary set. For example, if we have some ImageNet dataset, we can separate only, let's say, 500 of those categories and assume that we have a lot of labels for those 500 categories. And what we want to do is learn models and feature representations that will generalize or transfer to a new set of categories where we only have 1 to 5 examples per category. In self-supervised learning, which is a form of unsupervised learning, we assume we have no labels. All we have are unlabeled examples, and we want to learn effective feature representations. Note that in traditional machine learning, and to some degree in deep learning, there's also purely unsupervised learning where we can perform tasks such as clustering or density estimation. We'll talk about the distinction between self-supervised and unsupervised learning later. It's important to note that these are just common settings that exist. Recently, there's a lot of research that combines a lot of these different settings. For example, in few-shot learning, you can assume that you can also have unlabeled data as well. And that's again a different setting. It's important when you perform some work to understand what are the assumptions in terms of what data is available, both labeled and unlabeled, so that you can understand what setting you're in and leverage whatever state of the art exists in that setting. There are many traditional unsupervised learning methods that you may have learned about in your machine learning classes. For example, there are methods for density estimation, that is, somehow modeling the probability distribution over the input space. Again, we don't have labels, so it's not the conditional probability of the label given the data. It's just the probability over the data itself. So it's a joint distribution of the different dimensions in your data set. For example, for images, it's the joint distribution over pixel values that, for example, are drawn from when you have natural images. You can also have a clustering or grouping problem where you try to take your unlabeled data and group things that are similar and put things that are dissimilar in different groups. This is typically used either with a hand-coded similarity metric, such as Euclidean distance, for example, or there are methods to do what's called metric learning, where you try to learn a distance metric as well. If you think about it, there are other methods such as principal component analysis, which actually do some form of feature learning. That is, in PCA, you have some basis set of vectors that you're learning, and you can remove some of the bases that don't explain a lot of the variance in the data. And you're ending up with some reduced data sets that is a lower dimensional feature space. And this feature space somehow is a transformation of the input. And so it's some form of feature learning. There are other examples, such as sparse coding, for example, that you may look at. So we can try to categorize some of the unsupervised learning methods that exist. For example, modeling the joint distribution, the P of X, comparing or grouping things together, and representation learning. In the deep learning world, there's actually similar techniques for all of these different categories, but typically from a different perspective. Often, we really focus on feature learning, that is, learning an encoder or, for example, a convolutional neural network that takes the input, for example, an image, and outputs a set of features for them. And so for modeling the P of X, there are deep generative models. For comparing and grouping, there are metric learning or clustering approaches. And obviously, representation learning is pretty much what deep learning is. In these lessons, we'll really focus on the feature representation part, although we may talk about other unsupervised tasks such as clustering. Given label data, we know how to do this. We can design a neural network, for example, a convolutional neural network for images with some fully connected layers at the end. And we use the cross-entropy loss in order to drive backpropagation and optimization of the weights. So we have a forward pass here that makes predictions, and these predictions are compared to a one-hot encoding of the annotations. When we only have unlabeled data, though, it's not clear what to do. There are several different considerations that we might have. For example, what loss function should we use? Clearly, cross-entropy or mean squared error in the form of regression are loss functions that we've already developed. But it's not clear what to use here to drive the optimization of the features if we only have unlabeled data. We can also have maybe specialized optimization or training procedures that are better suited for unlabeled data. We can also have specialized architectures, for example, again, that drive some feature representation or dimensionality reduction. Finally, we're typically interested in transfer learning here. Why learn feature representations if you're not going to use it in some way at the end? What we typically want to do is learn really effective feature representations from very large corpuses of unlabeled data, and then maybe fine tune either just the convolutional neural network or maybe just the fully connected layers that we add at the end for a new task when we have maybe a small amount of labeled data. And so there are a lot of different methods, architectures, loss functions, and training or optimization procedures to deal with unlabeled data. However, there are a lot of recurrent common key ideas that reoccur across the literature. As a result, we'll focus on some of those. For example, in the semi-supervised learning case, where you have a small amount of labeled data and a larger amount of unlabeled data, there's a very simple idea that has been used for a long time, both in the deep and non-deep learning contexts. Specifically, you could take the training data that is labeled and learn a model through it. Again, using just normal deep learning and cross-entropy optimization. We can then take that model, which won't be that great, and feed all the unlabeled examples through it. The result of this is a set of predictions across all the unlabeled examples. We can then take only the most confident ones, that is, the ones that have a probability for a particular class that reaches above some threshold. We can then take that and convert it into a pseudo-label, that is, a one-hot distribution that looks very much like a label, but is not actually human annotation. So that's why it's called a pseudo-label. We can take these confident pseudo-labels and put them into the training set and retrain. Now we've added additional labeled data into our data set, and so hopefully we can learn a better model. Of course, these pseudo-labels will be much more noisy than humans, but hopefully this threshold will allow us to cull out at least most of the noise. Because of the noise, though, there's actually an interesting idea that you could do across views or data augmentations. For example, we could take unlabeled examples and perform augmentation of two types. We can have a weak form of augmentation, for example, color jitter, and feed it through the model to obtain pseudo-labels. We can then have much more aggressive augmentations, such as cutout that we've learned about before, and again, feed it through the model and obtain some predictions. Now here, instead of obtaining pseudo-labels for these strongly augmented examples, what we'll do is actually just take those predictions and use cross-entropy to train them. We'll train them through labels obtained from the weakly augmented data. That is, the idea is that we'll take weakly augmented data, obtain some pseudo-labels from them, and use it to actually train the predictions from strongly augmented data. The idea here is that The weak augmentation isn't so severe that the model won't have a good confidence or set of good pseudo-labels. But you're using strong augmentation to really make the neural network learn better. That is, you're using much more difficult examples to try to drive the features to be much more effective in the neural network, as well as the classifier. There's several different loss functions that we can use here, both cross entropy if you're using a hard pseudo label, or you can actually use what we've learned about before in the form of knowledge distillation, where you have a teacher network that's providing soft distribution pseudo labels and use it to train the predictions for the strongly augmented data in this case, using, for example, KL divergence loss. In the case of few-shot learning, where you only have a small amount of data, there's actually an interesting set of methods called meta-learning. It's called meta-learning because we're essentially learning to learn. What we're going to do is learn some neural network initialization that after it performs some stochastic gradient descent steps on a very small amount of labeled data, let's say 5 examples. So you won't perform that many SGD steps. You're learning an initialization that after you go through such process will be effective. And we'll talk more about this in the few-shot learning case. In the self-supervised or unsupervised case, there's what's called surrogate tasks. We'll actually come up with loss functions that come from weird tasks that we actually don't care about, but that hopefully drive the neural network to learn effective feature representation. For example, we'll rotate an image, again, an unlabeled image, and try to make the neural network predict which rotations we applied. Because we're the ones applying these rotations, we actually know the answer. So we essentially get the labels here for free. Now, this is a strange task because we don't actually care about it. We know what rotations we applied, but we're trying to force the neural network to learn some effective feature representations. And so we'll try to come up with a set of surrogate tasks that hopefully aren't too easy. That is, the neural network can't cheat in some way to do really well at these tasks and aren't too hard. That is, the neural network is able to learn something using the task itself. In this lesson, we'll talk about semi-supervised learning. Here we have a set of labeled data, again, a small amount of labeled data, typically, for example, 10 to 20 per category. And then we have a much larger unlabeled data. And so we'll try to understand what we can possibly do in order to learn both effective feature representations as well as classifiers. In semi-supervised learning, we have a smaller amount of labeled data and a much larger amount of unlabeled data. Again, this is because it's often much cheaper to get data, for example, by scraping from the web, rather than getting annotations, which requires human effort. And so the key question is, can we overcome the small amount of labeled data that we have using the larger amount of unlabeled data? Specifically, this is what we might want the semi-supervised learning algorithms to look like. On the x-axis, we show amount of labeled data increasing from left to right. And on the y-axis, we see the performance. Now, traditional semi-supervised learning methods look like the curves on the left. We had a particular performance obtained by supervised learning, just training on whatever data is available and not actually using unlabeled data. Semi-supervised learning algorithms, on the other hand, leverage unlabeled data, and so they can get some performance gains, especially when there's a small amount of labeled data. But they really plateaued out and started to underperform the baseline of just training on the labeled data that you have. On the right side, we see how we would like semi-supervised learning methods to perform, and to some degree, and on some data sets, currently do. What we have is the semi-supervised learning methods outperform the supervised even as we have lots of labeled data. This is because we have the additional unlabeled data, and you might think that you might be able to get some additional signal from that unlabeled data to eke out a little bit of extra performance, even beyond the supervised learning algorithm when you have lots of data. Of course, this gain won't be as large as in the low labeled regime, because in the low labeled regime, you can make much more effective use of the unlabeled data. There are several simple ideas that actually work decently in the semi-supervised learning context. For example, we can learn the model on just the labeled data. Of course, this model won't be very good, but it might be good enough, especially in the semi-supervised learning context where we have at least 10 examples per category. We can then use that model to make predictions on the unlabeled data. and we can add the ones that are confident into the training set, and then repeat this procedure where we then retrain the original model on the new training set and then make new predictions on the unlabeled data. You can combine this idea in order to make it much more effective with what's called co-training, that is, prediction across multiple views. This is actually a very old paper from 1998 that applied this, of course, not to neural networks, but other machine learning methods. In the deep learning context, we can just train as normal on the labeled data using losses such as cross-entropy. And then we could perform this pseudo-labeling approach across multiple views of an image. We can take an unlabeled example and perform augmentation on it, specifically two types of augmentation, a weak type and a strong type. On the weak type, we just apply the model, get predictions, and then threshold the examples by confidence. We'll throw out the unlabeled examples from the pseudo-labeling set if they're not very confident. Once we have the confident ones, we can obtain the actual pseudo-labeling. Rather than actually use the soft distribution, we'll convert it into a one-hot vector using argmax. There's other types of sharpening methods as well if we want. Now that we have a pseudo-label for this image, we'll also augment it again using a strong augmentation such as cutout. We'll again apply it through the model, get some predictions, and here we'll use cross-entropy, where we use the pseudo-label as the quote-unquote ground truth, even though it's not really human annotation, and it could be noisy. Again, the reason we have two branches here is because we can use weak augmentation in order to make predictions that are pretty decent. Because we're not augmenting the image too much, we're not going to destroy the predictions too much. On the other hand, the strong augmentations on the bottom will make it much more challenging for the model. And so that's actually what we're going to use for the backpropagation. We'll have hopefully much more certain and much more accurate pseudo-labels because we use weak augmentation, and we'll use those as the answer or the ground truth to train the bottom branch. This is an algorithm called fixed match that's pretty recent and has proven extremely effective in the semi-supervised learning context. In deep learning, there are several ways to instantiate this idea. In the previous slides, I hinted that there would be two stages, where we train the supervised model on the labeled data, and then we apply that model on unlabeled data, obtain pseudo-labels for those predictions that are confident, and feed those back into the training set. And again, we'll retrain the supervised model. The beauty of deep learning is that we don't actually have to do this in multiple stages. We can have this entire pipeline trained in an end-to-end manner. Specifically, we can have the mini batch consist of both labeled and unlabeled examples. For the labeled part of the mini batch, it goes through the traditional pipeline. We'll extract features, make predictions, and then use cross-entropy loss because we have ground truth labels annotated by humans. For the unlabeled examples, we'll apply two types of augmentations, again do feature extraction and prediction, and then use the predictions obtained on the weakly augmented label data, not in its own loss functions, but really as ground truth for the loss from the strongly augmented data. Specifically, this is what the loss function looks for the unlabeled part. We'll have a batch size B, for example, 64 examples, for the labeled part. And then we'll have a multiplication factor here, mu, for example, 7. So our unlabeled mini batch size will actually be much larger than the labeled part. And here we just sum up the loss function and average it. And our specific loss function will include the cross entropy loss H between the pseudo label Q hat B and our predictions from the strongly augmented data QB. And then we'll also have this indicator function, which looks like a 1, that only applies this to the predictions that have some greater than a threshold prediction. Even though this algorithm is extremely simple, it took a while for researchers to arrive at it as an effective semi-supervised learning algorithm. This is probably due to various reasons. One example is that pseudo-labeling in its vanilla form without performing data augmentation, that is multi-view pseudo-labeling, is actually not as effective. And this means also that we needed good data augmentation algorithms which also took a while to independently be derived. Finally, doing this in multiple stages is also not as effective as doing it end to end. However, there's always tuning and hyperparameters that are required to optimize this type of system. For example, the batch sizes used for most of the data sets were 64 for the labeled set and 448 for the unlabeled set. This actually turns out to be quite key. That is, large unlabeled batch sizes are actually required for this algorithm to perform very well. The confidence threshold for pseudo-labeling is also very important. If this threshold is incorrect, then the pseudo-labels will be very noisy. And so that means that the training may, in some sense, be corrupted. That is, your weights will be optimized using incorrect labels. On the flip side, if this threshold is too strict, then we won't have many pseudo-labels that are added, and so essentially you're not doing much with the unlabeled data. Other tricks such as specialized learning rates, such as cosine learning rate scheduler, were also key to effectiveness. Note that these hyperparameters differ for larger data sets, such as ImageNet. For example, here, the batch sizes were quite huge in order to get this to work well on ImageNet. In fact, these batch sizes don't really fit in single or even a few GPUs. You really need a cluster across many different systems in order to train such a model with such a large batch size. The confidence threshold is also varied, probably because the dataset is much more difficult. And again, if you're too strict on a difficult dataset, then you won't have many pseudo labels, and so nothing will really change beyond supervised learning. Finally, inference is actually done with exponential moving average of weights. Specifically, the weights at time t are some combination where you have a hyperparameter alpha times the weights at time t minus 1 plus 1 minus alpha times the weights of time t. Specifically, this can be seen as an exponential moving average if you work out the math. And so what you're doing is averaging or ensembling the parameters across the iterations. This turns out to make the training much more smooth or stable, as well as increases performance. If you look at the performance on datasets such as CIFAR 10, CIFAR 100, or SVHN, it's extremely strong. In fact, if you have 4,000 labels rather than 25,000 labels, you get a pretty small error rate, which is what these tables show on these datasets. Even on 40 labels, which again for CIFAR 10 is 4 labels per category, the performance degradation is actually not that bad compared to 4,000 labels. Similarly, for larger datasets such as CIFAR 100, you get a pretty gentle degradation. It still doesn't work very well for very few shot settings where you have, let's say, 4 labeled examples, but it's still much better than the current state of the art at the time. One of the nice things about pseudo-labeling based approaches is that they can be scaled up. Again, because it's easy to obtain unlabeled data, we can actually get some data sets with hundreds of millions or billions of examples. And we can perform the pseudo-labeling, again, using this teacher-student type idea, where we have the teacher model be trained on the labeled data. We then make predictions on a very gigantic unlabeled data set. We use that to train a student model, and then we finally fine-tune it on some data set in order to test performance. Again, here we have a semi-supervised learning setting where your labeled data set is actually pretty small in terms of the number of labeled data that it has. And so what you can see is that as you increase the data set, specifically the unlabeled data, into hundreds of millions or even billions, the performance continues to improve. And in fact, in some cases, we still haven't hit the plateau. There's a whole number of other methods that were developed before this fixed match algorithm and since then. Fixed match itself was derived from a number of iterations called mix match and remix match, which were much more complex variations of the same idea. It used things like temperature scaling or entropy minimization losses in order to make the training more stable. And rather than perform this strong and weak augmentation, it actually used an ensembling. That is, it performed multiple types of augmentations on the same image and then in order to improve the pseudo-labels, combined the predictions from each of those together. There's also interesting ideas called virtual adversarial training, which rather than performing hand-coded augmentations, actually learns adversarial examples through backpropagation, which we've learned about, in order to generate the augmentations. And then these are used through a pseudo-labeling type of approach. Note that there are other methods besides pseudo-labeling for semi-supervised learning, although recently they haven't been as effective as algorithms such as fixed match. For example, there's a class of algorithms called label propagation, which allow you to essentially learn, again, feature extractors, and then you can take those feature extractors and apply it on the unlabeled data and actually propagate information between the unlabeled and labeled data in a manner that respects, for example, the similarity in a clustering sense across the data. That is, we want the unlabeled examples to be labeled similarly to the labeled examples based on how close the features are to such labeled examples. This is somewhat akin to pseudo-labeling, except we actually leverage this clustering assumption, the fact that nearby elements should be labeled similarly. This is something that's akin to k-nearest neighbor, for example. But there's other optimization methods that can do similar things, but in a more sophisticated manner. So again, this is another way to perform pseudo-labeling, except maybe in a way that's more than just learning a model on the labeled data and applying it to the unlabeled data. You're actually using things like k-nearest neighbor type optimizations in order to propagate labels from the labeled data to the unlabeled data. In summary, we can now use unlabeled data to successfully improve supervised learning. This is quite a big deal because unlabeled data is very common these days. What's really nice is that the methods have actually gotten simpler, and now all they use are very simple ideas such as data augmentation and pseudo-labeling, and less necessary label propagation, although who knows what the future holds for more sophisticated ways to get better pseudo-labels. What's really nice is that the methods also scale to very large unlabeled datasets, although it's not really clear how many labels each unlabeled data is worth. That is, if we have a particular set or number of labels, let's say a large number of labels, how much unlabeled data do we need if we only have a fraction of those labels? It's intuitive to think that you probably need much more unlabeled data because you're getting a weaker signal, but it's not quite clear. It's also important to note that this area is not a solved problem yet. Although we can get very strong performance on academic datasets such as CIFAR 10 or 100, if you apply these methods to real-world datasets, which, for example, might have much larger amount of label noise or much more difficult input data, such as satellite imagery, then these methods perform much better than normal supervised learning, but may not perform as well as some of the academic datasets. So there's still a lot of exciting work to do in this space. In this lesson, we'll talk about few-shot learning, where you may only have a small number of examples per category, say 1 to 5, and we'd like to transfer from a larger labeled dataset in order to do well in this challenging scenario. In few-shot learning, the setting is that we have lots of labels in a base set of categories, and we have a lot of different categories as well, somewhere on the range of hundreds. And what we'd like to do is learn something that will allow us to learn effective classifiers for a new set of n classes, where n is typically 5 to 20, and in rare cases a little bit more than that. And so we'd like to generalize to this new n set of n classes, but we only have a few examples called a support set. Typically, we only have somewhere on the range of 1 to 5 examples per category for these n classes. And during inference, we have a query set where for each query item, we'd like to match it to which of the n classes does it come from. So this is called an n-way test. And again, n is typically somewhere from 5 to 20 categories. So you're not really distinguishing between thousands of categories, and this is because this is a challenging setting. We only have a few examples per category. And there's nothing special about the setting. This is just how the original papers on few-shot learning set it up. And it represents an interesting question of, can we learn on the n+1th class something effective even though we only have a small number of examples, leveraging the large labeled data set on a different set of categories. And again, recent research has broadened this setting in various ways that we won't cover here. But there's nothing special about this setting. This is just how it was originally set up. There are several approaches to few-shot learning. We can try to do what we always do, that is fine-tuning or transfer learning. We can learn a model on the large base set of classes. This includes both a feature extractor and a classifier at the end. And then we can optionally freeze the feature extractor. If you remember, typically we would like to do this when we only have a small number of labeled examples on the dataset that we're transferring to. This is because we don't have enough examples to actually effectively optimize the features themselves. We only really have enough to learn some classifiers. And then we learn the classifier weights for new classes using a small amount of labeled data. That is, we take the support set, which includes all of the classes and a few examples per class, and then we just train as normal. And we can use various tricks such as early stopping and so on in order to try to prevent overfitting. This is actually a surprisingly effective baseline. And over throughout the years, people have shown that if you can do this in an effective manner, that is, find the right hyperparameters and training schedule and so on, you can actually do quite well. Because we are only performing classification across a handful of categories, remember n in the n-way test that we perform during query time refers to somewhere between 5 to 20 categories. And this is the data set where we only have a handful of examples per category. We can actually use a different type of classifier that may be more effective in this case. Specifically, some research has shown that cosine or similarity-based classifiers, rather than fully connected linear layers, might perform better. On the left, you see the standard linear layer, where we have a set of weights, and we want to perform a classification task, that is output scores, that are then fed through softmax to output probabilities. We have a set of weights, and these weights can be seen as something that modulates the inputs. That is, we perform a linear weighted summation in order to calculate the scores. On the right, you see what the paper calls baseline plus plus, which uses a different type of classifier, namely a cosine classifier. Here, we're referring to cosine-based similarity metric. We still have a set of weights, but we can interpret each weight vector as a set of prototypes. That is, what the classes might look like. And we perform some similarity computation between these prototypes and the query. And the output of that is also fed to a softmax. Specifically, here's the cosine similarity metric. If you notice, this is actually similar to a dot product where you're just multiplying the input times the weight matrix or vector, but you're normalizing this by the size of these vectors. And so what you end up with is a unit norm comparison. That is, you're only looking at the angles between the feature vectors rather than incorporating how long they are across these different dimensions. And so this might actually provide better discrimination between a small number of classes because you're really focusing on just an angular difference rather than anything else. Again, because of the fact that we're only discriminating across a small number of classes, this ends up working better than a normal linear layer. And of course, that has something to do with the way the few-shot learning experiment was set up. And so in other settings, this may or may not work better. There are several downsides to the fine-tuning approach. The training that we do on the base set of classes, where we have lots of classes and lots of data or examples per class, all we perform is our normal optimization in order to do well on that large set of categories. But this does not factor the task into account that we will encounter during query or inference time. Specifically, there's no notion that we'll be performing a bunch of n-way tests. That is, we'll have a new set of n categories, where n is often smaller, from 5 to 20 typically, and we'll have a new support set, which are small labeled examples for these n categories, typically 1 to 5 examples per category, and then we'll perform these n-way tests during inference time. And so this is a general principle where we would like to align what we do during training with what we do during testing, with the idea that if we can optimize for it, this will provide much better generalization and you'll perform much better during actual test time. And so one idea is to just simulate what we will see during test time using the large labeled data set that we have. This is called meta-training. We'll take our large base data set that has many categories, let's say 100, and lots of examples per category, and simulate a set of smaller tasks which better mirror what will happen during testing, specifically the n-way k-shot task, where n is the number of categories, that's very small, from 3 to 20, and k is the number of examples per category, which again is small, typically somewhere from 1 to 5. In this case, you see n equals to 3 categories and k equals to 2 examples per category in the support set. And so the first training task will randomly sample a set of 3 categories and 2 examples per category, even though the base data set actually has more. And then we'll have a query set also sampled. The support set here is called the meta-train set, and then the query is called the meta-test set. And what we'll do is we'll have a model that forward propagates, that is, somehow learns something from the support set or extracts features from the support set and uses it to then make predictions on the query set. And then we'll backpropagate through that error if our predictions are wrong. And we'll do this many times. We'll simulate another training task too, and again, make predictions and backpropagate through some model. And then finally, after we do this, at the end, we have the actual test set where we can measure our performance on how well we do on the test set. You can also optionally pre-train features on held out base classes. Because we have lots of classes, let's say 100, we can take 50 of them, train across all 50 categories and all the label data available, just do pre-trained features, and then use the remaining 50 categories to perform this meta-training. Again, the testing stage is the same, but with new classes. The key thing here is that during testing, again, the classes that you see are completely different from anything you've seen in the training set and different than the meta training and meta testing set as well. There's a question of what we can learn across these various meta training tasks that we set up in order to then do well on a completely new set of categories where, again, we have in the test set a small number of examples, and then we want to, for a query set, map that each query element into the right class. So here are a few examples across various works in the literature of what you can possibly learn. On the left, you see essentially what's called the matching network, which just learns a feature extractor, such that when we feed the support set into those feature extractors and extract the features, and then similarly extract features for the query set, some hand-coded metric actually allows you to find the most similar class for each query item. Specifically here, you can use a cosine similarity or distance function and essentially make predictions for each query, which support element or which class does it most closely relate to. So here you're going to take the training task 1, the meta training task 1 that we set up, use the feature extractor to extract features from the support set. And again, this can be one example per category or many examples per category. But still, you essentially also extract features from the query and find for each query item what is the closest support set element that it matches to, and say that that query element is that class, one of the n classes that we have. And then you, again, take the training, meta training task 2 and do the same thing over and over again. During inference, again, you're set up with the same thing. You have a new set of n classes, and we have some support set that is a small number of labeled examples for those n classes. And we'll use the same procedure where we extract features from both and find for each query item the closest support element. You can also have a prototypical network shown in the middle here, where rather than matching each query item to the support set, you actually match it to a prototype or mean embedding. That is, let's say you have 2 examples per category in the support set, then you take for each class the 2 examples, you extract their features, and then you take the mean of those. And then you compare each query item to that mean rather than each individual support item. You can also have some generalizations of this where you have what's called a relationship network, which rather than learning some feature embedding that is then compared using a hand-coded similarity or distance function, you can actually try to learn how to relate in a more complicated manner each query item to the set of support examples that you have in the dataset. If you think about it, we can actually view this in a bit more general way. Specifically, we can view it as parameterizing an actual learning algorithm itself. That is, we're taking the meta training task one. We have a support set, and we want to perform some learning on that support set. And then we want to perform some predictions on the query set. Now, in the examples we've shown previously, this is very simple because all we're learning is a feature extractor such that when we feed the support and query sets, we can use some hand-coded similarity or distance function to figure out for each query element which one of the n classes it belongs to by matching it to the nearest support element. However, we can try to do this in a more general way. We can actually perform some form of gradient descent or weight updates on a model on the support set and then make predictions on the query set. Now, we've been using stochastic gradient descent to do this, where we take the negative of the gradient multiplied by the learning rate to perform the weight updates on the support set, and then we make predictions on the query set at the end. However, this doesn't necessarily have to be the case. Stochastic gradient descent is well known to overfit if we train it on a small support set where we only have a few examples per category. So we could try to broaden this notion and actually learn some update rule that's not stochastic gradient descent, but somehow is a function, a learnable meta-learning function that essentially takes in the gradients and does some update on a model. So we can have a more general view of learning how to learn. And there are several ways to look at this, both the examples that we've shown thus far and the examples we will show in the next few slides. But this is in general called meta-learning because we're learning to learn. We can take inspiration from a known learning algorithm. The examples that we've shown can be fit into this categorization. Specifically, the matching network, where we extract some features and then we perform a one nearest neighbor. That is, we take the query features and match it to the nearest support features, and whatever class that ends up being, that's the prediction we make for the query class. This is actually the same thing as a k-nearest neighbor, except it's a learnable k-nearest neighbor because we're learning the feature space. We can also actually learn the metric that we use, but in the cases that I showed, we actually used hand-coded metrics such as cosine, distance, or similarity function. The prototypical networks, where you take, let's say, 2 to 3 examples for a particular class and you extract features and then you take the mean of those features to get a prototype embedding, can be seen as a Gaussian classifier, where we learn a Gaussian model, a mean, and we can also do variance for each class, and then we essentially take each query item and match it to that Gaussian. But you can actually have some more interesting learning to learn kind of setups. Specifically, as I alluded to, we could try to learn gradient descent itself, namely the update rule. There are several flavors of this. One is called a meta-learner LSTM that views gradient descent, where we take as inputs a set of gradients and we make some updates to the model as an LSTM. Similar to an LSTM, we have some previous weights that we have, and then we take as input gradients, and then we output a new set of weights. This can be, again, mapped to the similar LSTM computations that we learned about, and we'll see this in the next few slides. There's also a simpler form called model agnostic meta-learning, which actually takes the view of just learning an initialization. That is, we want to learn some initial set of weights that after performing gradient descent, specifically stochastic gradient descent, on the support set, we don't overfit as much. That is, we can make better predictions on the query. And so you're not really learning the update rule itself, but you're learning an initialization that gets fed through normal stochastic gradient descent on the support set, which again is only a few examples per class. And we're trying to learn some initialization that maybe after stochastic gradient descent update rules doesn't overfit as much. There's other even more black box ways to look at a learning algorithm. These are called man and snail as examples, but we won't cover them. They're rather complex, and this is an evolving field. So let's take gradient descent. And let's say that we actually want to learn how to perform gradient descent. There's several parts to gradient descent itself. There's the parameter initialization. That is, what are the initial weights that we will use? And then there's the update rules. The output of this algorithm is parameter initialization and a meta-learner that decides how to update the parameters when fed the support set. Or alternatively, we can learn just the initialization and use the normal gradient descent. Here, the output is just the parameter initialization, and then we feed this initialization through gradient descent on the support set and hope that the initialization is good enough compared to, let's say, random initialization, such that it doesn't overfit as much. Let's take a look at how to learn gradient descent itself. That is, train a gradient descent-like procedure that can be applied to a model in order to update its weights given the support set. If you remember, gradient descent starts from some initial parameters, theta 0, and performs the following updates. The value of theta t, which is the set of rates or parameters at time t, is equal to theta t minus 1 minus alpha, the learning rate, times the gradient. What's interesting about this is that the gradient descent update rule actually looks quite similar to the LSTM cell state update rule. If you remember, the LSTM cell state update rule is as follows. The cell state at time t is equal to some forget gate that we compute at time t times the previous cell state, c t minus 1, plus some input gate calculated at time t times some update value, ct tilde. If you remember, the intuition is that the forget gate determines how much of the past cell state to forget, and the input gate determines how much of the new information to incorporate. And we can also have ct tilde, which is the new information, be computed as well at each time step. Here, Ct, or the cell state, if we map it to the gradient descent equation, is equivalent to the parameters theta t. That is, the cell state is the actual model parameters that we want to update. If you think about it, we typically have started with a 0 cell state, but we can look at the initialization, which we can actually backpropagate all the way through to the initialization of the cell state. And we can view it this as a learned initialization. That is, what initial weights should we start with, such that when we perform this learnable gradient descent update procedure on the support set, we'll perform the best on the query set. The state update value, ct tilde, can actually be mapped to in the gradient descent equation to the negative gradient. In this case, it's not anything parameterized. It's something we compute. Again, we can compute the gradients, and we can try to then perform the update. Forget and input gates actually have some really cool interpretations if we view this procedure as gradient descent. That is, the input gate is modulating how much of the negative gradient to actually update the weights by. This is just a learning rate, but it's an adaptive learning rate because we compute the input gate according to the LSTM equations conditioned on some information at each time step. So it's an adaptive learning rate method that's learned because we learn the weights that are used to compute this input gate. Similarly, the forget gate can be seen as an adaptive weight decay because it modulates how much we reduce the previous weights by. And so if we select a high forgetting that is computed again in a learnable way that has weights, then we'll essentially wipe out or reduce the values of previous weights. And so we're decaying the weights. If you look at this entire thing, that is viewing gradient descent as a learnable algorithm, and we map it to LSTM update rules, which has several learnable elements, namely the input and the forget gates, as well as the initialization, then we're essentially learning how to do gradient descent. Again, the key idea is that stochastic gradient descent, which is shown on top here, just taking the negative gradient, multiplying it by a learning rate, and adding that to the previous weights, has a tendency to overfit when trained on a support set that has a small number of examples per category. The question is, can we learn this gradient descent procedure that makes different types of updates and has an adaptive learning rate and adaptive weight decay? And can we do much better? Can we essentially overfit less when we apply this procedure to update the weights of our model on the support set? Here's a graphical depiction of the same thing. In this case, we can actually see how updating weights across gradient descent is actually just a computation graph. And that means we can actually backpropagate through this computation graph to update the weights of the meta learner, in this case an LSTM, in order to optimize those weights which determine, for example, how to compute the input gate or the forget gate, as well as what initialization to start with. We begin with theta 0, which again can be a learned set of initial weights that we start with. That is, we can backpropagate all the way back to theta 0 and update theta 0 itself. Again, in normal LSTMs, we often start with all zeros, but in this case, we actually want to learn the initialization. And for each mini batch of data, we take the previous parameters and output a new set of parameters. In this case, we'll have x1, y1 be the first mini batch. Again, this is few-shot learning, so the support set, that is the entire set of labeled data that we have, might actually fit into memory because it's such a small amount. In that case, x1, x2, and so on are all the same. We're applying the iterative algorithm to it over and over again, just like we do in gradient descent. Or x1 and x2 could be different if you can't actually fit the entire support set in memory. Regardless, we take the initialization theta 0 and the mini batch x1, y1 and compute the gradients. The input to our meta learner is this initialization as well as the gradients. And then it computes a new set of parameters, theta 1. This theta 1, again, is used to compute the gradients for a new mini batch, x2, y2, where we have, as a result, the gradients. And those gradients are fed to the meta learner, which takes theta 1, the previous parameters, and then updates them using these gradients, and so on. And so we can actually view this as a computation graph, where we're taking the mini batches of data and the initialization and progressively or iteratively updating the parameters. At the end, we have a new set of parameters, or the final set of parameters, and we just apply them to the test set to get our results. Now, because we perform the meta training procedure where we have a meta training, that is the support set that we're performing this learned gradient descent update procedure on, and the meta test, which is the query set, we can actually then make predictions on the query set and then have a loss function because we actually have the labels for those query and backpropagate through this entire chain. So we're literally backpropagating through gradient descent in order to update the weights of the LSTM. That is, again, the weights that determine the input gate values at each time step, the forget gate values, as well as the theta 0, which is the initialization. This LSTM viewpoint is actually quite general. We're actually learning a gradient descent procedure. However, it's not clear that all this machinery is necessary. Specifically, there are other competing algorithms that learn just one part of this, which is the initialization. That is, rather than changing all of the steepest gradient descent update rules that we've been using, we'll actually still continue to use it, but we'll backpropagate through that gradient descent procedure in order to learn an initialization. That is, we're asking the question, what initialization is robust to the standard steepest gradient procedure when applied to a small number of examples such that it doesn't overfit and can generalize to the query set. This is called MAML, or model agnostic meta learning. Again, we're using the same general recipe. We'll take our large labeled data set, split it into this meta training set where we have some training and some test sets, and then we'll apply gradient descent for, let's say, the first row here, the first part of the training set. And then we'll essentially measure our performance on the test set and then backpropagate through that gradient descent that we applied on the training data. And we'll backpropagate all the way through to the initialization. And so we're updating the initialization based on the training set and applying the normal steepest gradient descent on it, all the way to the test data where we make predictions and get a loss, and so on. Then we'll go to the next episode where we take the second row here of data, apply gradient descent, steepest gradient descent on the training data, measure our performance on the test set, get a loss, and backpropagate through it. So again, this is the same thing that we've been doing, except the key idea is that we're only learning the initialization. We're not learning how to actually perform the updates given the gradients as a learnable function. All we're doing is backpropagating all the way to the initialization and updating it. So we're trying to learn an initialization that's robust to applying steepest gradient descent to a small number of examples, and that can then generalize to the test set. Again, one of the key reasons that this is a good idea is that we can actually view gradient descent as a computation graph. That is, the procedure of taking the previous parameters, computing the gradients on a mini batch of data, and then updating the parameters is a set of computations And doing this iteratively creates a long computation graph that is sequential. And we can then backpropagate through this entire thing, either learning parameters of the update rules themselves, as in the case of LSTMs, or just updating the initialization, backpropagating this through the entire stochastic gradient descent set of iterations all the way back to the initialization. Of course, there's a lot of complexity here that we haven't gone through, and also you can only do this through some number of SGD iterations. Of course, doing a backpropagation across thousands or millions of iterations is not feasible. And so typically what we do is backpropagate only through, let's say, 4 to 10 iterations. This is actually not bad because, again, we only have a small amount of labeled data anyways, and so we'll be doing several epochs by then anyways. There are several trade-offs between the complexities of these two types of algorithms. The RNN or LSTM-based meta-learning is obviously much more flexible. It allows us to actually learn the update rules themselves. But this may incur some complexity and some consequences in terms of convergence of the algorithm, what it converges to, and whether it actually performs well. MAML, which is backpropagating only to the initialization, actually does have nicer properties because we're not actually changing the update rules. So we know that the procedure will converge, and we're not sure what it converges to, but we'll know it converges to some local optimum, just like normal gradient descent. Again, all we're changing is the initialization. And if it's not good enough, we can actually do many more gradient descent update steps. And so this is actually some trade-off between these two algorithms, namely the complexity or flexibility of what we're learning, as well as the results on things like convergence and effective performance, given that you're performing this. Because of the very simple nature of MAML, this is actually much more dominant these days. So in summary, what we've done here is taken a small amount of labeled data in our actual query time or inference time and are able to perform some update rules on the support set in order to learn a model that does well on the query set. And we did this by performing this meta training procedure, that is taking the large labeled data set that we had with 100 categories and many, many examples per category, and essentially split it up into many smaller tasks that we are backpropagating through. Now, again, this is an evolving field, and so there's lots of competing papers that do or don't use meta-learning, and even some recent methods that use things like cosine distance-based classifiers or just better pre-training and fine-tuning actually can beat meta-learning in many cases. However, what's nice is that MAML and similar meta-learning algorithms are very general and flexible, and so they can be applied not just to few-shot learning, but to other things like unsupervised learning and so on. In this lesson, we'll talk about unsupervised and self-supervised learning, where we have only unlabeled data and we'd like to learn effective feature representations so that we can fine-tune them for downstream tasks. For supervised learning, we have explored a number of architectures and loss functions in order to optimize this task. For classification, we often use fully connected networks at the end, which are then converted to probabilities through softmax, and we use the cross-entropy loss. For regression tasks, we can use other loss functions, such as mean squared error. The key is that we have labels, and these labels allow us to compute these loss functions, and we can use that to backpropagate through the network to update the parameters. In unsupervised learning, there's a set of traditional tasks that we may want to perform. For example, we may want to perform clustering, where the output is a set of clusters or groupings of data, where similar pieces of data are grouped into the same cluster, and dissimilar pieces of data are grouped into different clusters. We may just want to learn effective features, typically reduced dimensionality from the input. Here, dimensionality reduction has been looked at widely even before deep learning. And we just want to convert X, the input, into some latent feature representation, Z. Or we may want to perform density estimation. That is, we want to model the joint distribution over the inputs. In this lesson, we'll specifically talk about dimensionality reduction. That is, how can we perform effective feature learning such that we can then optimize them or fine-tune them for downstream tasks. We may talk a little bit about clustering as well. And in later lessons, we'll talk about density estimation, specifically using generative models. Unlike supervised learning, unsupervised learning only has the raw data as input. And so there's many things that we may want to learn, and it's not clear what is the loss function that we can use to drive this learning. So that's the key question. What can we possibly do with no labels at all? Especially in deep learning, where everything is formed through the loss function, which drives the gradients to update our parameters. One such task that we can use in order to learn feature representations that are effective is an autoencoder. Here, we'll use the same encoder-decoder architectures that we've talked about throughout in order to first convert the image into a small, low-dimensional compressed vector that is features. These features are low-dimensional embeddings that represent hopefully the most important aspects of the image. Given this bottleneck features, we'll perform a decoding step. We'll perform a reconstruction task. That is, we'll just try to reconstruct the input. This may seem strange. We already have the input. There's no actual need to reconstruct the input, but we're forcing the neural network to learn really effective low-dimensional embeddings that capture important aspects of the input. Once we train the system, we can actually get rid of the encoder and just use the low-dimensional embedding in order to, for example, fine-tune it to a labeled classification task. Again, the key thing is that here we can do this without any labels at all. We know what the input is. We want to reconstruct it. We don't need any labels. And this also allows us to use a very concrete loss function. That is, we can minimize the difference with mean squared error, for example, between the input and the reconstructed input. One of the key ideas here is the bottleneck in the middle. If that bottleneck is too powerful, that is, for example, the dimensionality is equal to the input, then actually the neural network can learn to just mimic the input. That is, it can learn the identity function. The key idea is that we're forcing it to compress the information into a small, low-dimensional embedding. Once we have effective feature representations, we can then use those features and add another linear layer in order to perform a classification task on a new task that we may have a small number of labeled examples for. Again, the key idea is that we can pre-train these features on large sets of unlabeled data and fine-tune them to a smaller data set. And in many cases, we can also freeze the encoder as well if we don't have enough data to fine-tune them. In that case, we're only updating the classifier layer, a smaller number of parameters, using the small amount of data. Another thing we can leverage is the clustering assumption. This is common in unsupervised learning, where we assume that high-density regions form clusters, that is, items or instances that are similar form groups or clumps in some feature space, while low-density regions, that is, regions where there's not a lot of examples, separate clusters, which hold semantic meaning. The key idea is that whatever feature space we learn, we'd like those feature spaces to have these kinds of characteristics. We'd like them to essentially have features that are similar for two similar items and features that are far apart according to some distance metric for elements that are different. And so this is what we're hoping. We're hoping that essentially whatever original feature space or raw input space we feed, once we output a feature space that's transformed using a deep neural network, we'd like that feature space to have this property. One thing that we can test this property with is apply k-means. For example, we can just optimize some neural network using, for example, autoencoders, and then see how well they partition the space. And we can use things like t-SNE, which we've discussed before, in order to visualize these feature spaces as well. We can learn an algorithm directly using this principle that can extract or learn features in an unsupervised manner. Specifically, we'll take the unlabeled data and feed it through a randomly initialized convolutional neural network. These features will be pretty noisy, but hopefully things that are somewhat semantically similar will have somewhat similar features. We'll take all of these features for a set of unlabeled data and apply an unsupervised clustering algorithm, such as k-means. Unlike a CNN, k-means takes the global structure of the feature space into account. So it will group things that tend to be similar in the feature space into one cluster, and things that are dissimilar into different clusters. And we'll use this, just as we did in semi-supervised learning, as pseudo-labels, that is, ground truth quote-unquote labels that we use to drive backpropagation. So the CNN will also have a set of linear and nonlinear fully connected layers and softmax function in order to make probabilistic predictions. and then we'll essentially have backpropagation through this prediction. The key idea is that forcing the neural network to group things that are somewhat similar in the beginning in feature space together and very dissimilar apart will improve the features. And then we'll do further iterations. We'll take the new features and then apply unsupervised clustering again. And again, this hopefully will produce even better clusters and hence better pseudo-labels. And then that will drive better feature learning and so on. Now, this loop will hopefully reinforce itself to drive the features to be better and better and better. Of course, there might be some issues. For example, you might have things like empty clusters. If the neural network essentially predicts that everything is in one cluster, then it can do really well and essentially have a trivial parameterization that always outputs the same thing. You can also have things like imbalance. If there's only one item per cluster for most of the clusters and then one cluster has a lot of things, then it'll just learn again to output that large cluster. And so this is a delicate balance between the feature learning part and the clustering part. But there are several engineering things that you can do that are described in this paper, which we won't go through, in order to try to balance this optimization. And in the end, really learn effective feature representations using unlabeled data alone. While a lot of these tasks have already existed before deep learning, for example, reconstruction is an optimization criteria for principal component analysis, and clustering has long existed before deep learning. We can actually generalize this idea into the concept of surrogate tasks. That is, we'd like to come up with tasks where we can get the answer or label for free in order to drive optimization and prevent the need for human annotation. These tasks, though, must also force the neural network to learn effective feature representation. And we'd like to engineer the task so that there aren't any trivial solutions or ways that the neural network can cheat to prevent it from learning effective feature representations. It turns out that over the years, a large number of such tasks have been devised, and they all have different characteristics in terms of how effective the features that are learned are, and this can differ both in terms of the level at which the neural network learns features, for example, low-level edge features versus high-level semantic features, as well as how well they can generalize to other tasks as well. One example is colorization. Given a red, green, blue, 3-channel image, we can actually just convert it to grayscale. This can be done using a hard-coded formula. And the input to a neural network will then be this grayscale image. And we'd like it to recolorize the image. Now clearly, this forces the neural network to have to understand something about what is in the image. Otherwise, it's really hard to colorize. For example, if you don't know that this is a fish or what type of fish it is, or if you have other objects such as tennis balls and so on, it's going to be really hard to apply the same color. And what's nice is that we know the answer. We already have the original RGB image. And so we can have the neural network predict the colorized image, and we can use, for example, a mean squared error loss function to drive feature learning. Another example is a jigsaw puzzle. We can take an image and separate it into 9 chunks that are non-overlapping. And so the input here is a set of image patches. But we don't give it the order of the image patches. Given 2 such image patches, let's say the center one and another one, we'd like to predict the discrete image patch location of the second one relative to the center. And so you could see this as a cross entropy loss across 8 different positions. Because for each image patch, you want to know which of the 8 non-center positions it's located in. Again, in order to put this together, the neural network has to form some representation that represents what is in the image in a semantically meaningful manner. Another one that's interesting is rotation prediction. We can have unlabeled images that we apply various rotations to. For example, we can have 4 discrete rotations. We then apply all of these rotations and force the neural network to predict what rotation we performed. And so the output is the prediction of the rotation amount. Again, because it's discrete, we could use a cross-entropy classification loss. Again, this is a task that we don't really care about in the real world, but will drive the neural network to learn effective features. There's a specific way that we evaluate the results of these surrogate tasks. Specifically, what we'd like to do is answer the question, how good are the feature representations that we learn in an unsupervised manner, and how well do they generalize to new labeled tasks? And so what we typically do is just take the encoder part. For example, in the rotation prediction, we don't actually care about the layer that actually predicts the rotation amount. And then we transfer it to the actual task. This is essentially transfer learning, where we use it to initialize the model of another supervised learning task. And we really use what we learned in an unsupervised way to extract features, such that we can add another classifier on top, typically a neural network or prior machine learning methods such as support vector machines. Often we limit the classifier to simple linear layers. This is because we're interested in how good are the feature representations that we learn and how generalizable are they. So if we're comparing many different surrogate tasks with each other, we don't want to have another confounding effect by adding additional complex transformations or nonlinearity. That wouldn't essentially tell us how good are the feature representations, but it kind of adds the additional element of training those additional layers. So typically we just take the features from the unsupervised surrogate tasks and then add a linear layer to whatever supervised classification task we'd like. Here's an example from the rotation prediction. This shows 3 different tasks: classification, detection, and segmentation. Typically, we show what the performance is using all the labeled data. For example, here you could see the row labeled as ImageNet labels. We can then compare to a whole host of different surrogate tasks. Here you see things like context prediction, jigsaw puzzles, colorization, and then from this paper, rotation prediction. What you can see is that the performance not just on classification, but even object detection is extremely competitive to ImageNet labels alone. That is, we can actually learn features that are almost as close to ImageNet learned features, which actually use labels to drive the cross-entropy loss. This is incredibly amazing, and only recently have we been able to do this. Another surrogate task that has achieved extremely good performance recently is instance discrimination. Specifically, we'll take an image, such as that of a bird on the top, and perform augmentation in 2 different ways. Again, these data augmentation algorithms are randomized. That is, you can apply different amounts of color jitter, different types of rotation, different cropping, and so on every time you run it. And so we'll perform 2 different augmentations with different parameters for the same image. We'll also have negative examples that are not the same image. Note that we're not saying it's not the same class or category. We can also have other birds and so on. It's just a different image. That is why it's called instance discrimination. We'll take all of these images and feed them through an encoder neural network that extracts features. And then we'll essentially set up a classification task where the features between the 2 augmentations of the same image should be driven together, and the features between augmentation 1 and the negative examples should be driven apart. This can be done with a dot product or similarity comparison between the different features, similar to how we did this in few-shot learning. And so what we have here is positive example, which is the same image augmented in a different way, and negative examples, which are all other images. There's some interesting questions here of where the negative examples should come from. And we'd like to consider things like efficiency. For example, we don't want to recompute all the features across our large unlabeled dataset just for the purpose of getting negative examples. We also want to have some nice characteristics of negative examples. For example, they shouldn't be too easy or too hard, and so on. In fact, there's a lot of research that we won't talk about here that tries to even select what negative examples should we subsample from the larger unlabeled dataset. There are several ways to extract the negatives. Here, we show 2 methods. On the left, we can have an end-to-end method where we essentially have an encoder that's shared, and we have the key, which are the negatives, and the query. And what we can do is essentially just within a mini batch, use all the other examples in the mini batch as negatives and perform end-to-end gradient updates to the encoder across all of the examples in the mini batch. In other words, here we're just using the mini batch items that are not the current image that we're focusing on as the negatives. There's some downsides though, because this ties the number of negatives that you're sampling from to the mini batch size. If your mini batch size is too small, then you won't have that many negatives or your negatives may not be diverse. In the middle, we see a memory bank approach. Rather than sampling from the mini batch, we could try to store negatives across the iterations in a memory bank, specifically a queue. In order to make the sampling of negative examples easy and efficient without having to redo feature extraction every time on the large unlabeled dataset, we'll use the notion of a memory bank. Specifically, we'll use a queue that comes from previous mini batches, which holds the features extracted from those mini batches. So given a new mini batch of data, let's say containing this bird, we'll feed it to the feature extractor, and we'll actually, at the end of this iteration, put it in to the queue. So we'll pop out older items and replace them with these newer features. And in future iterations, when we sample negatives, we'll actually just sample images from this queue. Now, the key idea is that we don't have to do any extra feature extraction because as the iterations go by, we've already extracted those features since we need them for the backpropagation, and we're just storing them so that we can later use them without having to recompute them. There's some issues here that might occur. For example, the features might be stale. If you're pulling elements from way in the front of the queue, which means that they're very old, and what we have is that these features are extracted using a long number of iterations away in terms of the weights, which have since been updated as the iterations went by, then the feature space is no longer the same. There might be some staleness in the feature space. But actually, it turns out not to really matter because this queue won't be that large compared to the very large amount of data sets that we have. In order to alleviate this, we can also use the idea of an exponential moving average of weights. This is similar to what we've seen before, and here is called a momentum encoder. The key idea is we want the key encoder to move slowly so that when we put them into the memory bank and use them to compare against the queries, it won't be as different. Here, the key encoder is set to m, which is a hyperparameter often set to 0.999 times the parameters of the key encoder, plus 1 minus m times the parameter of the query encoder. Here, only the gradients flow through the query encoder, so only those are updated. Really, the momentum encoder is just a moving average of the query encoder. Again, this slows down its evolution for the key encoder so that essentially when using it within a memory bank across iterations, it won't be as different. This method has turned out to be extremely effective. Specifically, if we learn unsupervised feature representations on the ImageNet data, and then we freeze those features and learn an additional linear layer whose parameters are optimized using ImageNet labels, we get actually quite close in performance. That is, we get 71.1% accuracy as opposed to 76.5% if we jointly train the features and the classifier using all the labels. Again, we're only using labels for the 71.1% accuracy to train the linear classifier on top of the frozen features that were learned in an unsupervised way. So this is quite surprising, and only recently have we been able to achieve such strong performance. What's even better is that these features tend to generalize better to other tasks. If we can see for the VOC object detection task, we actually achieve higher performance using instance discrimination. Again, this shows that features that you learn in an unsupervised way, when used to initialize other tasks such as object detection, are actually more generalizable in some sense, which is quite surprising and exciting to see. In summary, there's a large number of surrogate tasks and variations that we can use to learn really good feature representations using unlabeled data alone. This includes contrastive losses, which work across image patches or context or instance discrimination. And there's many different types of loss functions or training regimes that we can apply, some of them more efficient than others. The two that have become dominant and extremely effective are for unsupervised learning, contrastive losses, and when we have semi-supervised learning, pseudo-labeling losses, where we have essentially the learned model applied to the labeled data, making predictions on the unlabeled data, and that gets used to drive a cross-entropy loss. You can also use soft knowledge distillation, where you don't make the prediction a one-hot for the pseudo-label. And I haven't covered all of these methods, but a lot of these methods work, and it's not clear which one is the best currently. What we do know is that data augmentation is now key. These methods are used across almost all of these unsupervised learning and semi-supervised learning methods. And maybe unfortunately, methods tend to be sensitive to the choice of data augmentation. So there's a lot of recent work exploring how we can automatically learn data augmentation or be able to figure out at least what data augmentation to use. Overall, these advances have been extremely exciting and have really only occurred recently.